Doncs primer intentarem treballar com un científic del CERN, més o menys. Després, com us ha explicat l'Eugeni, intentarem aprendre què és el mesó de zero i com es comporta o quina és la seva naturalesa. En mesurarem alguna de les seves propietats, en aquest cas el light. No l'hem acabat. Anirem a una altra sala que està millor que la que he estat avui perquè és una cosa impressionant, on ens connectarem amb gent del CERN, hi haurà un parell de monitors que ens explicaran una mica com és la vida. Juntaran i sortirà alguna cosa decent. Aquest any, cada any canvia, aquest any ens toca parlar, a part de nosaltres, aquesta conferència del CERN, hi haurà gent de Florència, Birmingham, Cincinnati i Programa. Vale, doncs, aquesta cosa ja no... Bueno, hi ha una U, una D, una C, una S, una T i una B. La B encara la veiem. Vale. Ho sento. Doncs què és el mesó D? Doncs el mesó D de 0, en aquest cas, com ha explicat l'Eugeni, és un mesó, per tant són dos quarts, que està format per un charm, que és un C, diguéssim, una partícula com a tal, i un app, però com si fos la seva antipartícula. Quin temps de vida té això? Temps de vida vol dir el temps que tarda aquesta partícula de caure. Sabem que és una partícula amb una mica de massa, us han dit al voltant d'un parell de masses d'un protó, i com que pot caure en coses més petites, decau. El teu temps és això, 10 a la menys 13 segons. Doncs 13 zeros i un 1 al final, el temps que tarda, o sigui, de segons. I això provoca, com que té aquest temps de vida relativament llarg, que puguem més o menys mesurar el que fa abans de decaure. Però té un problema, que com us han dit abans, detectar partícules neutres o tracejar amb traces partícules neutres és impossible, ja que no interaccionen elèctricament, per tant, problema. Com ho solucionem? Doncs sabem que el D0, una de les seves propietats és que té una probabilitat de decaure en un pió i un cau. Un pió negatiu i un cau positiu. Doncs buscarem, com que el D0 es crearà, volarà una mica i després decaurà, i aquestes dues partícules les podem detectar, les podem trassejar i arriben als nostres calorímetres, si juntem, diguéssim, d'alguna manera l'energia d'aquestes dues partícules, podem arribar a trobar un D0. Què passa? Doncs a l'Lhcb, bàsicament, hi ha dos beams de protons, xoca protó contra protó, a una velocitat molt alta, i això provoca moltes partícules, però coses exagerades al voltant. Tenim a vegades col·lisions de 400, coses així, coses bastant exagerades. I com us he dit, les carregades són més fàcils de pillar, les que són 0 tenim problemes. Fotons, neutrons, etc. tenim molts problemes. D'aquestes moltes partícules que es creen, algunes ens interessen. I com també us he dit, la manera que fem nosaltres és esperar que decaiguin i quan decauen, agafar els seus productes. Però clar, la probabilitat que decaiguin en una cosa o una altra és la probabilitat donada per una teoria, que és el model estàndard, com us han explicat. Aquest model estàndard us diu el D0 té una probabilitat d'un tant per cent de decaure en un pió o en un caó, però també pot decaure en moltes altres coses. I això bàsicament és el que fem els físics del CERN, que és intentar buscar, en el cas de l'Lhcb, coses molt rares, coses d'altres magnituds de 10 a la menys, per intentar provar aquest model estàndard. Perquè com més, si vas a coses molt petites, pots trobar partícules que no t'esperes i, per tant, noves partícules, noves coses que no teníem previst a la teoria, podem generar un nou model. D'aquestes col·lisions, nosaltres som capaços, aquestes col·lisions de protó-protó que creen tantes coses, som capaços de reconstruir-les. L'Lhcb, que us l'he ensenyat abans, està format de diverses coses. Un tràquer al principi, té tràquer aquí, que és el Velo, que és el Detectors, que és el tràquer, dels millors tràquers del món, diguéssim. També té aquí, després del Magnet per transformar les partícules, etc. Té un parell de rits Detectors, que rits és Serenco, Flight, que era un amplitat, no? Una partícula, quan passa en un medi, que era un cono de light, si va més ràpid, un cono de llum, si va més ràpid que la velocitat en aquell medi, etc. Tenim aquí els calorímetres, que seran els que ens serviran. En aquest cas nosaltres, com que anem a D0 caó-pió, els caons i els pions són mesons, però mesons dintre els hadrons. Per tant, la que ens interessa és aquesta... Ens interessa aquesta fletxa, per tant, tenim un hadró que el detectarem al vertex locator, deixarà un co de llum aquí, deixarà una traça aquí al TT, es torcirà pel magnet, deixarà més traces al C3, tornarà a fer un co de llum i després s'arriba al calorímetre fins a l'últim, fins al calorímetre hadrònic i d'allà deixarà la seva energia. Vale, doncs una mica us he dit abans, farem servir un programa del CERN que es diu RUT. Veurem els senyals que deixen les partícules que estem buscant i altres que no ens interessaran tant. I en el programa veureu com pitjar una línia, veureu una cosa similar a aquí, que no ho veieu gaire bé. Però si pitjar una línia us donarà informació sobre la partícula. Aquí hem de diferenciar dues coses. Nosaltres estem buscant D0s anant a pió, caó. Tot el que no sigui un D0 anant a pió, caó, per nosaltres no ens interessa. I el que no ens interessa, el que volem treure, en diguem background, i el que ens interessa, que és el D0, en diguem senyal. Vale, farem... Heu vist que cada un té un número? Alguna té un número a la vista? Que aixequi la mà, sisplau. Hauria de començar pel 30 i acabar al 50 i alguna cosa? Sí? Vale, doncs... Aquest exercici està separat en dues parts. Ara us explicaré com es fa per introduir, etc. Però el vostre número l'heu de fer servir quan us digui. La primera part us donaré cada un de vosaltres, cada parella de vosaltres tindrà 30 esdeveniments i la gràcia és buscar un D0 en aquests 30 esdeveniments. Ja us explicaré com es fa. I la segona part, a lloc de 30, hi ha algú que ha fet el mateix que heu posat a la primera part, però amb 20.000 events, i intentarem buscar alguna probabilitat, en aquest cas, del lifetime del D0. Vale, doncs em sembla que aquesta ja l'heu vist abans, aquesta presentació. Busquem un pió i un caó que vinguin al mateix punt, que estiguin, veureu que hi ha un lloc a les imatges que hi ha la col·lisió que està molt al principi, que està a la part del velo, a la part frontal, i d'allà haureu de buscar una partícula que no veureu, que es desplaça una mica i després es generen dues traces, dues línies, una serà del caó i l'altra del pió. I us donaré una manera que podeu fer el càlcul de les dues masses quan l'ajunteu i al final ha sortit al voltant, el D0 té una massa al voltant de 1,8 GeV o 1.800 metres. Anireu fent això, anireu guardant les masses d'aquestes dues partícules que heu reconstruït, del pió i el caó, i ho anireu ficant en un histograma que ja us diré com es fa. I ara, si voleu, podem començar l'exercici. Hauríeu de tenir tots vosaltres una cosa així de davant? Sí, correcte. Algú no ho té? Important, algú no ho té? No? Que aixequi la mà qui no ho tingui. Primer, abans que feu res, heu de triar l'idioma, trieu anglès, l'heu de pitjar, perquè després si no us deixeu autocompletar. Pitgeu anglès, fiqueu, si voleu, com que sou parella, fiqueu els dos cognoms, un el nom i l'altre cognom, jo fiqué el meu. No serveix per res, vull dir, no servirà, només perquè els agrada. Grau, fiqueu estudiants de batx, segon de batx o alguna cosa així. Jo fico postdoc, doctorat, i després aquí heu de buscar el número que teniu a les taules. El 30, sí, i el 50 i alguna cosa i el flamenc. Sí? Teniu un número vosaltres? No, cada un té un número. Vale, doncs fiqueu el 30, busqueu el 32. Si teniu, no ho he dit, però si teniu algun dubtes, a darrere teniu tot ple de gent perquè us ajudi, Perquè a part de mi, hi ha més gent que està a l'altra sala que estan movent-se per aquí. O sigui, aixequeu la mà i som bastants per ajudar-vos. Quan hagueu triat una combinació, per exemple, jo triaré el 19. Guardem i pitgem aquí, a l'1. I s'obrirà alguna cosa. Correcte? Tothom està aquí? Eh? A on? Fiqueu el que vulgueu. No ens faig per res. Fiqueu segon de batxillerat. Dos vaig. No, és una cosa que haurem d'enviar després, al final. Després inventarem els vostres histogrames i no és una cosa de rellevància, perquè sabeu que és vostre i ja està. No es fa estadística, no es fa res. Vinc costarà una mica, perquè la resolució de l'ordinador i això no ho guarda, però bueno, ja farem alguna cosa.
Agraïm que posin
Segon de batxillerat. Estem tots aquí. Hi ha algú que no està aquí? Important. Hi ha algú que no està en aquest pas? Ha triat el seu esdeveniment, ha ficat el nom, cognom, els dos cognoms, el grau, el seu número i ha pogut anar aquí? Hi ha algú que no? Segueu la mà, sisplau. Estic deixant la veu. Tothom està bé?
No, falten uns quants.
Quin problema hi ha? Digueu el vostre número. Ja veig que molts heu començat a lligar. I no ho podré gaire molt bé perquè he ficat el display aquí perquè veieu, perquè ho podeu veure perquè si no la gent no veurà res. Però bueno, us explico una mica més com va això. Aviam, cada vent, nois, ei, oh! Vosaltres heu posat un número i aquest número té 30 vents dintre. Podeu canviar de vent amb aquestes dues fletxes, cap endavant, cap endarrere, vent 1, vent 2. No els heu de fer tots. Millor qualitat que quantitat. Si veieu un que hi ha 50 milions de línies i no sabeu trobar-lo, el següent, no hi ha problema. Vale, com ja veig que alguns ja sabeu més o menys com va, podeu moure això com vulgueu, cap amunt, cap avall, amb la ruleta també us apropeu i us allunyeu. I després tenim un parell de trucos aquí, que és... Podem amagar tot el que és el detector, que està molt bé, sobretot quan ja aneu cap al final i ja més o menys heu pillat com va això. I també podeu fer-lo transparent, que està bastant bé al principi, mola bastant. Després podeu, amb aquestes coses d'aquí, podeu ficar-vos en un eix en concret. Podeu ficar-vos en un eix en concret, aquest és l'eix X, l'eix Y, l'eix Z. Podeu jugar amb això, també podeu girar amb el ratolí, arrossegant, etc. Sí, la qüestió és anar... Jo veig bastant diferent de la llengua. La qüestió és... Si veieu que les línies s'ajunten, hi ha línies que van cap a dalt i cap avall i s'ajunten més o menys... És que no em deixa veure això. No feu trampes. Heu de buscar més o menys el punt en què hi ha els feixos que es creuen, diguéssim. El feix de proton no els veieu, però després, quan xoquen, es creu un cop. Heu d'anar més o menys al principi i d'aquí heu de buscar dues partícules. Jo us dic, si baixeu, és que no feu gens bé, però si baixeu una mica, aquí baix hi ha d'haver una llegenda que us diu quin color és cada cosa. Aquí baixeu, aquí hi ha una llegenda que us diu què és cada cosa. Recordeu que estem buscant un pió i un caó, i em sembla que són verd clar i rosa vermellós.
Joder, tio, no pots...
Sí, la qüestió... El truco... Ara us diré quan fa un. Aquí hi ha una posició i apareixen dues partícules. Sí? Que faré una. Ja, escolteu, nois, ara això. Quan hagueu trobat dues partícules que us semblen que venen del mateix punt però apareixen del no-res, que és la gràcia, més o menys, han de ser més o menys verdes i... que és un color vermell lilós. Després hem de comprovar que aquestes dues partícules de veritat venen d'un desert. I com ho fem això? Doncs, aquesta gent del CERN, si petxeu sobre una línia d'aquestes, aquí a l'esquerra veieu tota la informació. Es veu? Es veu tota la informació de la partícula. El que farem per saber si les dues partícules aquestes provenen d'un de zero és guardar-les. Per tant, guardeu una partícula, agafem l'altra, guardem l'altra partícula... Ah, no, he agafat l'altra. Guardem l'altra partícula i diguem calcular. Què passa al calcular? Que el programa és suficientment intel·ligent per calcular la massa i l'energia de les dues partícules i ens donarà una massa. He fixat al calcular aquest i m'ha sortit un número. Aquest número ha de ser semblant a la massa del D0, que us he dit que era uns 1.800 i alguna cosa. Per tant, veig més o menys que té una pinta i dic, vale, doncs, l'afegeixo a l'histograma. Sí, l'afegeixo primer i després puc dir, ja em dibuixa l'histograma.
Això millor al final.
No, podeu dibuixar-lo com vulgueu, no hi ha problema. Però, clar, amb un punt... Sí.
Un cop l'hem afegit a l'histograma ja podem passar.
Podeu passar de vent, quan aneu finint l'histograma, sobretot afegiu-lo, si voleu mirar l'histograma podeu mirar-lo, si no, no, aneu a dalt i aneu al següent event. Tampoc cal fer-ho de tot, ja us ho dic. Més bé qualitat que quantitat. Normalment es creen a la part del principi. La gràcia és que a la part del principi té la col·lisió protó-protó, i després es crea una partícula que és el de 0, que no veu, i de cau en verd. No. Si veieu el calo per anar a la ratlla, perquè el calorímetre d'aquestes partícules que el calorímetre que hi ha a la ratlla, la gràcia és que hi ha una mica de podeu veure, costa molt veure, la gràcia és jugar una mica, això és el detector de veritat, això és una veritat de col·lisió del CERN, no és mentida, que algú s'ha dedicat a passar-lo de manera visual. Cada un en tenim 30. N'hi ha alguns de fàcil i n'hi ha alguns de molt difícil.
No, però saps el que vull fer? Però és que aquí m'apropo i comença ja el...
Ah, sí, avui.
Vull veure un horitzontal.
Diferents events no s'ha de dir. Diferents events.
No, vaig que
Algú no sap
Coses calculades.
Vale. Aviam. Vale. Sí, tothom està en aquella cosa que us he deixat allà? En el D0 exercise, tothom hi és? Ara us explicaré com va. Sí, tothom? Algú que no hi és? Bueno, si estan en ello? Explico una mica què farem aquí. Com us han explicat abans, bueno, si ens han atropellat una mica el que us anàvem a preguntar, el D0 viu 10 elements 13 segons. Ok. I com hem dit, també viatja molt ràpid, que és a la velocitat de la llum. Ara bé, si algú de vosaltres ha agafat un paper i ha fet una mica de càlculs, veurà que si multiplica la velocitat de la llum pel temps que decau, la distància que recorre en aquest temps és 0,03 mil·límetres. Jo us dic, a Lhcb és impossible que vegis alguna cosa amb 0,03 mil·límetres. Però som capaços de veure el temps de vida d'aquesta partícula, d'estudiar-lo i de donar un valor precís. Per què?
Es dilata.
Normalment és més difícil que no us diuen a l'anterior, però bé. Sí, el temps es dilata i, per tant, en lloc de parell viu al voltant d'uns 10 elements 13 segons, però per nosaltres viu una mica més i, per tant, recorre més distància. I al final recorre una cosa que és més o menys un mil·límetre. I això, el temps aquell, diguéssim, el temps del seu decaïment és el que estudiarem en aquest exercici d'ara. Vale. La probabilitat de decaure, no sé si ho heu vist mai, depèn, és una exponencial. Heu fet distribucions exponencials? Crec que sí. Sí? És una distribució com aquella d'allà i només diu, aquesta distribució pel temps de decaure diu que hi ha una probabilitat que aquesta partícula, que encara de 0, decaigui en aquest temps. És molt difícil que decaigui en un temps molt gran i és molt menys difícil que decaigui a un temps més petit. És molt fàcil. I d'aquí nosaltres, si fas una recta, el logaritme base 10 per una exponencial, et surt una recta, bàsic, i d'aquí podem trobar nosaltres la pendent. I aquesta pendent en diem el temps de vida mig. Això és, d'alguna manera, no és ben bé la meitat del temps, però la mitja que la majoria d'aquestes partícules decauen. I això és una propietat que ens interessa molt a nosaltres. Vale. Doncs aquí, en aquest exercici, en lloc de tenir, vosaltres heu fet 30 events cada parella, aquí hi ha, sembla que són uns 20.000 events, però que ja estan triats. Algú ja s'ha dedicat a trobar el D0, ja ha agafat un pió i un caó, el resultat ja ha dit, mira, això em penso que és un D0. Però tenim un problema, que vosaltres n'heu fet 30 i potser no us heu equivocat, no crec que us hagueu equivocat. Però si en fas 2.000, potser t'equivoques. Agafes una cosa que tu penses que és un pió i un caó que dona una massa que et penses que és de 0, però potser no és de 0. I això en diguem background. I intentarem ara, com fan com ens dediquem nosaltres a fer física partícules, com que nosaltres no ho fem un per un, com ho fem vosaltres als centres d'eminents, i fem per ordinador, l'ordinador s'equivoca. Perquè nosaltres l'ordinador diem unes que passi això, que passi això, que passi això, però pot equivocar, pot agafar coses que no són correctes. I ens dedicarem a separar el que nosaltres considerem que ens importa, que és la senyal, d'aquestes coses que la màquina, l'ordinador o algú s'ha equivocat a agafar i que en diguem background. I amb això podrem estudiar les propietats. Fitarem, d'una manera que ara us explicaré, la distribució de vida i podrem trobar un valor d'aquest temps de vida mig. Quan tinguem això fet, després tindrem punts tipus això. I aquesta línia és la línia que en realitat és el D0, és la línia de veritat del temps de decaïment del D0. I em direu, uah, però això està bastant lluny. I us diré, clar, és que jo ara mateix us està dient que jo tinc un protó-protó, tinc una col·lisió protó-protó, que surt d'un D0 i decau. Correcte? Però jo puc tenir una altra cosa, puc tenir un protó-protó que crea una partícula més pesant que un D0, una lambda B, una partícula molt pesada que després de caigui en un D0 i un altre cop en un protocaó. I nosaltres en cap moment el podem distingir què passa. Com ho farem això? Doncs farem servir el paràmetre d'impacte, que és aquesta distància d'aquí. El paràmetre d'impacte és la distància entre, diguéssim, la distància més curta entre la trajectòria de la partícula reconstruïda al D0 a la línia de protó-protó. Això què vol dir? Per exemple, si jo tingués, si aquí al protó-protó es creés una partícula molt pesant, volaria una mica, aquesta partícula molt pesant decauria en un D0 i potser estaria per aquí, i el D0 cauria en 2 més. Per tant, aquesta distància ens pot ajudar a reduir molt aquests events que no volem, aquests events que el protó-protó no produeixen un D0 directament, sinó que produeixen una altra cosa i després el D0. I això bàsicament és el que farem. Veurem com tallant aquesta variable, diguem, no permeto que aquesta variable sigui més gran que o més petita que, veurem que tallant això podrem anar provant més el temps de decaïment. Després, aquí el que heu de fer és, ara us ensenyaré com va, però heu d'apuntar el temps que trobeu per cada cop que feu un tall d'aquests, del paràmetre d'impacte, agafeu un paper i boli, sisplau, i heu d'apuntar el temps i l'error. Perquè el programa ho dibuixa, són 10 mesures, no són més. Vull dir, no hi ha... El programa, com veieu, ho dibuixa, però no us diu el temps. Vale. Ho farem un... Vale. Comencem. Aquí tenim unes quantes variables, allà a l'esquerra, que és molt difícil, que és el PT, que és el moment transvers del D0, que també potser després el podem tallar, ja veurem. La vida mitja del D0 també, que això és el que estem buscant, però en aquest cas també pot ser una variable, però no ho farem servir. I l'impact paràmetre del D0, que és el que estarem fent servir per anar reduint aquest background de D0s que no volem. Comencem primer plotejant la massa del D0. Com veieu, aquesta massa teòricament hauria de ser una gaussiana, una distribució normal. Però, si veieu, si sabeu, la distribució normal ha d'anar a 0. Aquesta no va a 0. Aquesta va com una línia que està al voltant de 2.000. Per tant, tot això d'aquí baix és background. Són coses que ens hem equivocat nosaltres a agafar el pió i el caó, els hem ajuntat i hem dit, mira, això no és de 0, però això en realitat no és de 0. Vosaltres estàveu buscant, si costa de veure, però són 1.850 per allà al mig, i vosaltres estàveu agafant coses d'aquí, però la màquina potser s'equivoca i agafa un d'allà. Sobretot quan no saps la massa de la partícula et pots equivocar. Li farem que la fiti, i això fa 2 fits. Fitar vol dir que l'ajusta. Ajusta primer el senyal, ajusta, considera que hi ha un background, aquesta part d'aquí, aquesta línia vermella que veieu, considera que tot això és background i la part de dalt la senyal. I quina és una manera de treure tot aquest background? Doncs és una manera molt fàcil, que és dir background subtraction, que és dir, mira, jo només em quedaré tot el que hi hagi d'aquí, d'aquest rang, perquè sé que tot l'altre és mentida, sé que tot l'altre algú s'ha equivocat i és background i no em serveix per res. Per tant, si fixo més o menys, això cada un que triï el rang que vulgui, però jo triaré, no sé, 1.840 i potser 1.890. Cada un que triï que ajusti el màxim model possible. Jo ho estic fent ràpid, però hauríeu de pensar una mica. Quines penseu que a partir d'aquell moment segur que no hi ha cap de 0. Jo crec que està bé. I ara el que faig és plot distribution. I en plot de distribucions. Explico una mica si voleu. M'agrada la distribució que tenia abans i ell amb el fit m'ha dit més o menys quant de senyal i quant de background tinc. Sí. A la dreta és el PT, és aquella variable allà a la dreta, que és el moment transvers. La línia blava és la senyal i la línia vermella és el background. Per tant, si quan acabeu l'exercici penseu una mica, potser podeu solucionar una mica després de treure el background. La part d'aquí baix no en feu cas i aquest d'aquí és el que a nosaltres ens importa, l'hiperparàmetre. Nosaltres ara començarem a tallar del que estem, que el valor és d'aquí, a 1,5 fins a 4. i anirem tallant. Ara no he fet cap tall, o sigui, ho he permès tot, i li diré, vale, doncs, amb totes aquestes dades, digue'm quin... El programa calcula d'una manera una mica més complicada del que ara mateix us puc explicar i calcula un lifetime, calcula una vida mitja. I em dona aquí baix la vida mitja, em diu la vida mitja és 0,47 més menys 0,045. Això és el que heu d'anar apuntant vosaltres per cada cop que talleu. Vale. Si baixeu més a baix, això no m'ho permet. Ja. Sí. I ara, a més en baix... No, i ara us dic jo. I ara aquí posa save, posa baix. A baix d'això posa save result en fit. Això ho guardarà i us farà l'histograma que us he ensenyat abans. Que no em va bé. A baix fica save result en fit, correcte? Doncs això el que farà és aquest histograma d'aquí. Us sortirà d'una pestanyeta i podeu anar fent. Sí? Save resultant fit, això el guarda el resultat, save plot, i aquí te'l ploteja. El punt no el veiem perquè està aquí dalt. Vale. És veritat, a vegades això d'aquí no surt bé i surt una recta que va on vol. El que heu de fer és canviar una mica el rang que heu agafat. Perquè el programa és una mica tot. Això és el primer i us sortirà un punt. Tothom té un punt? Ara anem al següent. El que intentarem nosaltres ara és fent servir aquesta distribució, anirem tirant de l'1,5 que està aquí fins al menys 4, anirem tirant enrere. Jo us aconsello que de 1,5 a 0, aneu de 0,2 a 0,2. Agafeu això d'aquí, 1,5, ho baixeu 1,3, plantegeu un altre cop el mateix. Si us hi fixeu, el número de vents disminuirà perquè estem tallant, estem perdent a vents. Estem perdent més o menys de background de senyal, però estem perdent a vents. Torneu a demanar més o menys que el rang sigui coherent amb el que vosaltres. Quiteu, si us surt una cosa bé, guardeu, plantegeu i aneu fent així. Heu d'arribar més o menys de 1,5 fins a 0, de 0,2 a 0,2, la feu amb 0,1, i després jo us aconsello que a partir de 0 aneu de 0,1 a 0,1. Sobretot, aneu apuntant al paper el resultat i l'error. Al final, són 10 apuntades, una taula de 10 valors, que es mou. Algú no en té res? Està perdudíssim?
Tindràs més errors o menys?
So as we interpret the graphic, we see that this indicates a normal probability distribution for the mass of the D0 particle observed. And we believe that that probabilistic interpretation has something to do with quantum uncertainty and the Heisenberg's uncertainty principle. We understand that to be, I suppose, an inverse relationship between the knowledge we have of the mass of the particle against the momentum of the particle. If we know more about the momentum of the particle, then we know less about the mass and vice versa. And we understand that the normal distribution arises from that. However, on the specifics of the mathematics behind that, we have not investigated.
Yeah. So exactly. I mean, this uncertainty principle is somehow combining either knowledge of your momentum and where you are in a certain place, or related with like your energy and the time for which you exist. And so I guess you guys from this therefore have deduced that the width of this is related to how long something is around for. So actually, if you plotted this peak for example, a proton, which is the most stable particle, then you would see something which is like infinitely narrow, essentially. So it's that, reverse relation. But that's exactly the idea.
Cool. So maybe what
Seguiu?
you see as well. So what you see here right now is the result of putting everything together, but we can see actually how it looks like when you first, just analyze the first 30 events, and then we keep adding data. Okay, so this is what we are going to see right now. So you see that at the beginning, we really saw nothing. Basically, we saw just fluctuations of the data. But as soon as we keep accumulating events, independent events, we really can see the pattern starting to form here. And then it's when we can really see that this actually peaks at the mass of a known particle, which is, as you have said very well, the neutral D meson, right? So you can see that, putting the 4 together of different people that work in parallel, we can actually get at the end much more information.
¿Veis que está juntando los datos de todas las universidades? Han salido incluso vuestros nombres por ahí. Y eso es el resultado combinado de momentos 3000, más y más y más. Y veis que el pico cada vez es más claro en D0.
Yeah, and it's really that point of to be certain that what you're seeing is not, I mean, you saw that maybe just one of your data sets, you could not with any significance say that you really saw a peak there. So it's really this idea of adding enough data until you have a very high significance that what you're saying is not just some lump in the data which means nothing, but it's a real physical effect. And that's essentially also the reason why it's what we're always trying to do is get more and more and more data, which gives us more and more information on smaller and smaller sizes of peaks, for example. And this is because everything is probabilistic because we're living in, a non-deterministic universe. So
okay, cool. I think that's a good summary of the first part of the exercise. So maybe we can move on to the second part. Let's try to see if we can hear Prague. So maybe you can, guys, explain us what you have been doing for this second part of the exercise where we try to measure the lifetime of this particle.
All right. So first of all, we'd like to pitch.
So you guys could try muting your audio on that end and just unmute your microphone, maybe.
All right. Do you hear us nice well? Well, I suppose you do.
Can you try to?
I think it's good.
Go ahead.
Yeah.
Please,
okay.
Can you...
So we're finally online, probably. So we'd like to wish you a nice day. And the second exercise was about that we wanted to see the actual decay time of the zero meson. And the point of that was that we first gotten our hands on quite a large set of data from all of our research or experiment, maybe. And then we had to remove the background, which was pretty much the particles that were not the ones we were looking for. So we had to make certain cuts in the research field so that we could get our D0.
Okay, nice explanation, thank you. So maybe guys, you can also tell me what's the result you get at the end for the measurement of the lifetime of this particle.
We're sorry, we just didn't hear you.
Yeah, there's a bit of echo again. So what is the value you measured for the lifetime of this D0 particle? Do you have it with you?
Yeah. Well, the problem with our volume was that we actually it turned out that the volume of ours, when we counted out, the volume from Prague was quite inconclusive because we didn't actually get to the volume that was expected. Our result was actually pretty accurate in the sense that the differences between the single results from each person were quite similar, but they didn't really come that close to ones that we wanted to reach. So there was some similarity, but I can't say the results were conclusive in our case.
Okay, that's an interesting observation, I would say. But before going in detail into that, I would like to ask the other institutes to share also, basically, if you can give us the value you measure so we can actually plot them and compare the results properly between different institutions, okay? So Prague, for you, I got this number from your professors, which is 0.458, and the error is 0.001. Is that correct? Okay, cool. Then maybe we can move to Barcelona, who I see are connected again. Hi guys, can you hear us? Hello, Barcelona. I think they are trying. Yeah. We hear noises, so.
Birmingham?
Sorry, were you asking for Birmingham?
Yeah, so if you can just read out the value that you guys measured for the lifetime.
So we don't, unfortunately, we weren't as coordinated as some of these other groups, so we didn't have them recorded, but we got a number of values. You guys want to shout out some of the values you got?
Yeah, maybe one of them, that would be enough.
Yeah, one's fine.
I got 0.417.
0.47 picoseconds was one that we got.
What's the error on that? 0.47.
Okay, and we got another one? Yeah.
I think 0.6. I can't remember the answer.
0.6 picoseconds, okay. Yeah.
0.46
Okay, so we got 0.46 as well. Plus or minus.
And can you give us also the uncertainty you got in one of these measurements?
0042.
0.042. Okay. That's good. Then let's move on. Firenze, can you tell us your result?
Hi. Yes, our result was 0.4052, and the uncertainty was 0.0054.
54. Okay, cool. Thank you very much.
You're welcome.
Barcelona.
Yeah, let's try with Barcelona again.
Can you now hear us, Barcelona? Yes, you're faint, but we can hear you. Yes. Can you read out what you got for the lifetime measurement?
Hey, that's better.
Yeah.
Okay, 4189 is it, right? Cool. And what's the uncertainty on this value that you got? Okay, great. So I think we have them all. Let's try to combine these. Well, to compare it for now. Okay. So let me see if you can...
Després d'això, els hi podeu preguntar més o menys el que vulgueu. Penseu que voleu preguntar a algú que està al CERN quasi permanentment. Si fa fred, això t'ho puc dir jo.
Firenze, can you maybe try to repeat your value because I think I got it wrong, sorry.
Yes, it was 0.4052.
Okay.
Okay.
Yeah, and the error 0.0054.
Yes,
Okay,
that's
cool.
correct. Okay.
Then, yeah, it's okay then. Okay, then let me share all the results compared. There we are. Right, so you should be seeing this. Can you wave if you see now a plot with various points and errors on it? I will take this as a yes.
Yes.
Okay, we will take that as a yes, right? Okay, so what are we seeing here? So these are the different institutes. You can read here, look for yourself. These are basically the points you gave us with the uncertainty. So you can see that we have actually quite a different type of results from the different places. And just for comparison, we put here also what we call the wall average. So this is basically the combination of all the different measurements from different experiments that we've had so far. Okay, so this is basically the most precise measurement we have. Okay, so you can see this is this red line. Some results are a bit above, one is even below. Let's try to understand what happened here. Maybe, maybe Barcelona can try to explain us what they are seeing in this plot and how do you interpret these results? Why do you think, let's focus on your result. What do you think about it? Did you have to do anything special to get to this, let's call it good value? Fair enough. Okay, cool. Yeah, that was the purpose of the exercise, so I think that's good. Okay, good. Maybe we can come back then to Prague, who actually I'll really comment a bit on this number. So you guys basically have the most precise result, but we could also say that actually it's the one
El que està dient la Carla, diu, els de Praga és els que han tingut el resultat més precís, perquè les barres d'error el que ens diuen és quina és la precisió de la nostra mesura. Clarament els de Birmingham deuen haver analitzat 10 o 12 esdeveniments i per tant el resultat que els dona té una incertesa estadística molt gran. Nosaltres i els de Florència més o menys n'hem analitzat els mateixos. Els de Cincinnati sembla que n'han analitzat tots i aquests sembla que hagin analitzat totes les dades del CERN i més enllà, perquè clar, no tenen cap error. Efectivament. És molt bon punt aquest, que el vostre company diu això és que s'ho han inventat. No sé si s'ho han inventat, però per això és molt important sempre tenir gent en diferents llocs fent el mateix experiment, perquè al final tu has de poder veure que algú altre és capaç de reproduir el mateix experiment i tenir uns resultats que no han de ser iguals, però han de ser consistents. I si hi ha alguna cosa que no és consistent, s'ha d'entendre. D'acord?
And more systematic biases in our data. So actually, your statistical error is actually quite small, which means
aquí el meu amic físic teòric ja diria que ha descobert física més enllà del model estàndard, perquè això no és compatible.
Because you have a larger statistical error, it's probably telling you that there you have less entries, because the less data points you have, the larger error you normally have. But this difference, therefore, may be more of a systematic one to do with taking into account events which are essentially background and not events that we want. So this was maybe slightly alluded to by Barcelona when they said that they did put in some cuts to remove certain types of events, and these are so these are going to be Ds. So we have Ds here, and we see in the peak that we saw before that it's pretty what we would call clean. So you saw a nice peak. However, not all Ds are made equal, and you will be having problems if you are also including Ds, which don't come directly from when you've got, your protons coming together and your Ds are coming out, but that are coming from a secondary decay. And including these could then be biasing your measurement. So if you haven't removed them, you have more statistics, you have less statistical error, but you probably have more systematic bias in what you're looking at. So that's probably the reason.
Yeah, I agree actually.
Yeah. Cool. So yeah, that's actually a nice thing to learn, because first time you do a measurement, you kind of don't realize about these systematic effects that could be affecting it, and it's quite important. So it's not just about accumulating more and more data, which is important, but at some point you also have to kind of try to repeat the experiment maybe in a different way and so on, so you can actually wash out a bit these systematic effects that your own experiment have.
Which are super, super, super subtle, right? There's no way that any of you guys could possibly know this without having a lot of experience in the field, but it is so that's absolutely 100% fine what you have done, because it's, you wouldn't know this unless you spend a long time working in a specific detector, but it is, however, a good example of the subtleties of understanding what you're measuring and the effects that you can have by including events which may be biasing you. Yeah. Questions?
Cool. Well, yeah, I think that was a good discussion about the experiment, and I think we have. Let me stop sharing, because I think I've seen we have a visitor with us today. Yeah, maybe Anthony's. Can you hear us? Are you there with us?
Yes, I can hear you. Can you see me?
Yeah, we can very well, and we hear you also loud and clear. So maybe you can explain where you are.
On the phone at the moment. Okay. It has changed a little bit. So I'm not sure exactly what you're saying, but what you should be seeing behind me is part of the Lhcb detector. I'm actually sitting 100 meters underground, right at the heart of the experiment.
Wow, that's really cool. So maybe you can show us a bit what you have around and explain what we are seeing with you.
So I'll try and give you a very quick tour of the experiment. So you used tracks in order to find the d particles and measure the d0 mass. And behind me, what you see over there, sort of maybe greenish box, is actually the velo detector, or what used to be the velo detector that's really at the heart of the experiment. So if I just change my camera to the other side. Okay, has it actually changed? It would be good if I could see what is going on. There, I can see a little bit now. Right, so let's have a quick tour around Lhcb, right? So we start...
Ara ho podem veure perquè vam deixar de prendre dades a final d'any i estem actualitzant el detector. La setmana passada el Pere i companyia estaven desmuntant coses aquí i de fet ell ha vingut aquest matí
the hole that you see over there, plugged in, is where the beam pipe normally comes from the LHC. And on this side, what you see is the velo tank, because the velo detector is actually part of the vacuum. And just behind it, in blue, what we've got is the first Cherenkov detector, the first bridge detector.
Nosaltres al primer exercici estàvem mirant per trobar el xoc de col·lisions i d'on sortien el velo.
Is a gas and mirrors, and we use a Cherenkov light that is generated to identify the particles. Up there, you can see the cables for the photon detectors that are coming out. These are the low voltage cables, the thick ones where they carry most of the current. And on the lower side, what you see is mainly optic fibers. These are the cable equivalents where they carry the signal, because we try and digitize the signals at the front end and then use optic fibers to transfer that to the computers that we have quite a distance away. And behind each one, what you see here sort of in green, maybe I'll move a little bit further back to get a better picture, is the Lhcb magnet. So these are the coils of the magnet that can create a uniform field, and we get a dipole magnet.
L'imant que ens permet fer el camp magnètic, que ens fa drossar les partícules per poder mesurar càrrega i moment.
And it's actually using about 5 megawatts of power. So we have to circulate water inside the magnet in order to keep it at a reasonable temperature. And we have cooling towers upstairs where we actually cool down the water. The water comes in at sort of ambient temperature 20 degrees and then goes out about 60. Now, can you see the beam pipe? What is left on the beam pipe over there? So the bit that's sticking out is part of the beam pipe, and the beam pipe would continue this way. So this part through the magnet is actually the view of the particles, if you like. The collisions happen on that side, inside the velo, and the particles just fly out going through the magnet. Now, unfortunately, I cannot show you much more in this view, because we have taken out all of the tracking detectors. There used to be a tracking detector right in front of me, and there used to be more tracking detectors further down, but Lhcb is going through a major upgrade in the next 2 years. So we have just taken all of the detectors out, and we're planning to install new ones. And further back, what you see, sort of probably just a little bit of gray, is the cover of our second Cherenkov detector, just to make sure we don't damage it, so we cannot see it very well. Okay, so let's move a little bit and get a slightly better view of the magnet. This the blue part that you see over here is the iron that we have in order to contain the magnetic field. And then behind, in that green box, are actually the photon detectors of the second Cherenkov detector that we have. And further back, if you can see these sort of copper-like boxes, these are part of the muon chambers. This is where we detect the muons. So just showing you a little bit more, you can see our radiation shield. A large part of it has come off. It looks a little bit like a pyramid, maybe. All of these concrete blocks. You can see some of them. This is to protect the people and the electronics that are on the other side of this wall from the radiation that we have on this side. So when the experiment is running, we can be on the other side of this wall, but not over here. And as you can see, I'm quite a distance above the floor, about 6 meters above the floor, because of course the beam pipe is not at floor level. It's the middle of the cavern, which is, well, quite big. Not as big as Atlas and CMS, but quite big. You can see the crane up there that we use to carry things around. And everything that's coming in and out comes in and out through that shaft on that side. And it's being used quite heavily at the moment. So this is a little bit of what the underground area of Lhcb looks like. You can see the crates here. Sorry, the racks. We've taken a lot of the things out already. A lot of power supplies and other equipment normally. So there's a lot of work happening at the moment, and a lot of the things are being taken out. And probably in about 3 to 6 months, we're going to start putting all of the new detectors back in order to do the upgrade of the experiment.
Cool, that's really nice, Anthony. Thank you very much for doing this tour with us. And I'm sure now the guys from the different institutes have a lot of questions.
Teniu alguna pregunta? Que aixequeu la mà.
We have just seen. So maybe we can start with Birmingham. Do you have questions for Anthony's?
En anglès, perquè és a l'Anthony.
Birmingham, can you hear us?
We can, they're working on it. Yeah.
No hi ha cap més pregunta?
Vale. So I think the question is, so what is this upgraded detector for?
The upgrade detector. So the detector has a certain has the ability to take data at a certain rate. So far, the detector that we've been using, I mean, all of the components have been good enough to take, on average, just one interaction, one proton-proton interaction, what we call per bunch crossing. The beam in the LHC is separated in bunches. They come every 25 nanoseconds. And when two bunches collide, each bunch contains about 120 billion protons. On average, we get one proton, just over one on average, actually hitting one other one. Imagine 120 million protons in a bunch, and only one of these 120 million hits one on the other bunch that has a 120 billion. So we can take a rate that, if you like, if there was a collision at every interaction, we're going to get something like 40 million collisions per second. But that rate is a little bit slow because we're looking for a lot of processes that happen very rarely. So the plan is to upgrade the detector to be able to cope with more data and not have one proton hit another, but have 5. And in that case, we can take 5 times more data. But that makes everything a little bit more complex because now that you've got 5 protons hitting 5 protons, you get a lot more tracks in the detector. And we need to have better resolutions, more granularity in a lot of the systems, plus the amount of data that we create is more, and that needs to be transported to the computers. So a lot of the detectors are being upgraded in the sense they become better. And then we also upgrade all of the links from the detector to the computer farm.
Perquè ho sabeu, ara, o 2018, estàvem guardant 0,6 gigabytes per segon a Lhcb. Després de l'upgrade 2022, estarem a 10 gigabytes per segon.
Hi. Yes. We wanted to ask a bit more about, I suppose, your career leading up to working in a particle detector. Some of us are interested in perhaps what steps could you take to get such a position. And also, as a bit of curiosity, you mentioned being irradiated earlier in your tour, and I was curious what the dangers of being irradiated are in working at a particle detector.
So do you want to take
in terms of career, I'd say I did the usual things, physics degree, PhD. I was always curious about particle physics and then somehow ended up in the field. I was lucky enough to get a permanent position at the right time. In terms of radiation, what is going on is during the accelerator, while the accelerator is running, of course, we have a lot of radiation in this area because of the particle collision. As soon as the accelerator is off, all of that goes away because there are no more particles flying about. However, the bombardment of the materials of the detectors with protons and neutrons can actually change the materials from the standard materials into radioactive ones, which means that after you've been doing that for a while, there is a low-level radioactivity happening because of all of this bombardment. And it's not particularly, it's not a lot, but one always tries to minimize the exposure. So me sitting here is fine. Me being in there is not so fine.
Yeah. Thanks, Antonius. Maybe just to add also to the point of on the career point, so people who are particularly interested, there are various also internships that you can do with CERN. So there is, I think, an internship even for high school level, I'm pretty sure was mentioned. So maybe we can send that link on the chat at some point or by email. I'm sure you can ask your local like coordinator if they have information on that, but we can also send it in the chat if you don't have access to that. But it's some like a certain high school program, and then there's also summer students. I mean, like so obviously the general path is also in my case, like on Carla's case also, that we do physics at university, and then at some point you either choose to do your master's or your PhD. But you can also do like summer school internships, summer student internships, where you just go to like CERN when you're still just in your undergraduate, and spend the summer there as well. So that's also a nice way to get into it. So there's a couple of like kind of interning programs that are also nice to look into if you're interested in getting more involved.
Thank you.
Yeah, thanks to you, Cincinnati. Maybe we can then try with Firenze. Do you have questions there?
Yes, hello everyone. I would ask, what are the discoveries you are expecting from your new experiments, and what are the results you are, also expecting from this new equipment? Yes, that's my question.
Okay, maybe I can try to answer this one. So, okay, basically at Lhcb, what our main physics program is similar to what you have been doing today. So basically, we try to precisely study the properties of particles that we already know of. Okay, so like in this case, you were working with the D meson, and we are also experts, if you want, on the B sector. So different kind of meson that has a big quark in it, that we call B mesons, and we study all the properties you can imagine of these guys, basically checking all the predictions from theory. And here it's very important that we are very precise in our measurements, right? So as you are seeing in your own results, if we have few data, the results are not so clear. So we need to keep accumulating data. And that's, as Anthony said, that's why we want now to be able to take 5 times more data per second. And then what we are expecting, well, that's kind of the magic of research, that normally you don't really know what will be there because no one has been there before to look,
we
right?
Say what we want to be there, though.
Exactly. We know what we want to see, which is basically something that was not really predicted by the theory, right? So that would make things much more interesting if you want.
I mean, I mean, this is somehow, we have this theory of particle physics that we call the standard model, and that explains the universe very precisely in certain areas, but we know it's not the complete picture because there's still things it can't explain, such as dark matter. So we know that there has to be a hole in this theory somewhere, and the question is just where is that hole going to appear? So, we're doing these precise measurements exactly to see if we see a measurement which wasn't predicted by the theory, and then we can say, so this could be the start of like new physics, or kind of the second order effects of new particles that we haven't ever seen before. And that's somehow like what everybody at CERN is driving towards, to find physics beyond what we currently know, which can help explain things in the universe that we currently can't explain.
Yeah, and actually just to add, we are right now in a moment at the Lhcb where we are kind of having some measurements that, they are kind of deviating slightly. Yeah, deviating slightly from this theoretical predictions. So we are really willing to get more data to see with a better precision where this exactly goes. And actually, it's a very interesting moment for us at the Lhcb and also with this upgraded detector. Thanks for the question. That was very good. Let's move now to Prague, maybe. Do you guys have questions over there?
That Planck particle exists?
Oh, sorry. Can you just start the question from the start again? You just cut off for the first 5 seconds.
Okay. She asked me to repeat. So, do you think the Planck particle exists or not?
The Planck particle? Is that what you are asking for?
Yeah. Yep.
So I don't know if this is entirely within our realm, but essentially any particle that has been hypothesis. So you have different theories, right? Which may. So we have the theory that we know is an actual description of the universe, of this standard model. And then you will have theorists who then come up with new theories, which, if they were true, they would explain away some of the problems we currently have. For example, you have supersymmetric theories, which would offer a good explanation for dark matter, for example, as well as some other undesirable stuff that we still have left within our standard model theory. So there is a lot of theories put out there. However, there is not necessarily currently any theory which is particularly well motivated, which we wouldn't then have already seen. So a lot of these new theories, they really thought we were going to see something as soon as we turned on, or as soon as we went up in 2015 to even higher energy, and then they were convinced they were going to see new particles. And the fact that we haven't means that there's not really currently now, I don't think, any particularly compelling theories that we have kind of in the literature that we've currently seen or not seen. So probably the short answer is no. Yeah. Thanks for the question.
Yeah, okay. Let's try to quickly check if Barcelona is still with us and have any question. Barcelona, can you hear us? We hear something, but you're really fine. Can you try to approach the microphone, maybe? Yeah, that's better. Yeah. Okay, maybe Antonis, do you want to answer this one? Thank you.
There's already an acronym. There's the FCC, the Future Circular Collider, and people talking about making a 100-kilometer long ring where we could have an accelerator that would give us to, the next sort of energies. There's a plan to maybe start with an electron-positron collider at sort of higher energies that we ever had before, and then study some of the things we kind of already know, like the Higgs particle in detail, and then eventually build a new hadron collider that will do HAT-TV. These things take a long time to design, and they cost a lot of money. So the LHC will run until 2035, 2040, and maybe by then we'll have already some good plans for the next one. One can start digging a little bit earlier. To make a 100-kilometer long tunnel, it takes some time. But this is sort of the time scale that we're talking about, somewhere between 2035 and 2050.
Thanks, Antonis, and thanks, Barcelona, for the question. So I think, we should move on.
Oh, sorry, I think there's one more. Was that another question? Go ahead. Very quickly. Yeah.
Okay, so I can try to answer that one. So basically, as Elunet was saying before, there are theories, right, that predict somehow if there's dark matter, how would it be produced and how it could also interact with the particles we already know, right? So there are theories that predict if this dark matter could be created at the proton-proton collisions that we have at the LHC, how much this would happen. And then, once you have this dark particle, that's the way we call them, what happens with them? Do they later disintegrate again into standard model particles, like we were seeing with the D0, or maybe not. So there are experiments that look for this exactly at the LHC. Lhcb is not specialized on this, but we actually have some studies about that as well. And then the major players here are basically Atlas and CMS, who are the two big, we call them general purpose detectors. These are the ones that also discover the Higgs. So they have better capabilities for this. And actually, one of the cool ways I think they look for this, then I've always find it very interesting. So these detectors cover basically all the surrounding area of the interaction point, right? They are kind of hermetic, we call them. So they basically see anything that comes out of this proton-proton interaction. And one of the ways to search for dark matter is to basically sum up all the energy you are measuring in your detector and check if there's anything missing. That's what we call missing energy. So if you really see that there is an important amount of energy that it's missing, this could be basically because there are particles that are produced in your collision that you are not able to detect because they don't interact with your material. And this would be a clear signature, for instance, of dark matter. So basically, we have been studying this, and so far we have not seen anything similar to this. And so what we do is basically keep putting limits, constraints on what could be the mass of the particle or the energy, etc. Thanks for the question. That was interesting. And as much as we would love to keep talking with you about other questions, we are running a bit late, so we really need to move on to the next part. So I think we can first thank Antonis again and say bye-bye to him. Thank you very much, Antonis.
Bye.
Bye. And then, Elmet, you can...
Yeah, so this last part is just to kind of wrap up the whole day and give a bit of a summary. There's a quick, fun quiz. And this is,
farem un quiz ràpid.
Fun being the main word, so it's not obviously graded in any way, but it gives you a chance also to kind of, summarize yourselves also what you've learned or not. So you can just answer this yourselves, either in your head, piece of paper, etc. I'll just show the question, and then you have like 10 seconds to think of the answer, or you can also discuss between yourselves, and then the answer will come up. There's, I think, 7 questions in total, and I need to share the screen, so if you bear with me half a second.
In principle, I think you should have a paper answer sheet with you in your institute, so you can now take that and grab a pen and just be prepared to answer. If you don't have it, don't worry. As Elmet said, you can just think it in your mind as well.
Share application.
Yeah, it should work. Okay, so you should be seeing now the start of our game, just saying rules of the game.
With nothing else.
Can you please wave if you see it?
Yeah.
Cool, thank you very much.
Video's not working. Yeah, cool, perfect. So, so as I just said, 7 questions each, and it's just going to be multiple choice. As Carla also said, and I forgot, you should also have this been given to you by your institute, so maybe also translated if that's relevant. And then as we go along, we'll be revealing the answers on the fly. So let's see how well you guys do. Ready, set, go. Which particle is the mediator of the strong force?
A, neutralino, B, Z boson, C, gluon, or D, quark?
Okay, and the answer there was the gluon. So it's the gluons which mediate the strong force. Okay, next question. How much of our universe is matter? How much of our universe is matter or energy of which we know nothing about? So the stuff that we don't know about.
Yeah, I'm sure you have discussed about this during the day at the institute,
Yeah,
so
we
probably
have,
it
if
sounds
not-
familiar.
It's not. It's a bit of a hard question, but so it says 95%. So 95% of our universe is made up of dark matter, or dark energy is about 75% dark matter, and then the remaining 20, whatever that is, is dark energy. And this is simply stuff that we know must be there because we've seen it via astronomical observations, but we don't know what particles are causing those deviations. So we just don't know what more than half our universe is made up of. And that's one of the really key questions actually that we try to answer at the experiment here at Lhcb at CERN. Okay, what is the power consumption of the LHC, the sailors? So it can be the same as a small village, or maybe all the households in the Geneva canton, maybe the whole Switzerland or the France. What do you think? Let's see the answer. Right, so it's the same as the all households in Canton Geneva, and this is basically half million people, sorry.
Per culpa d'això, quan corria l'ACC a l'hivern, el paràvem, perquè no hi havia suficient energia per a tothom per escalfar-se, etc.
It's getting more and more difficult though, so be prepared.
What does the Higgs field do? So I'm sure you heard about the Higgs particle, and this particle is a manifestation of the Higgs field, but what is the Higgs field responsible for? Why were we so excited to see this particle? Okay, and the answer is that it solves the origin of mass. So before we had verified that the Higgs existed, the Higgs field is essentially the only way that we had in our current theory to give particles mass within the theory without violating a bunch of stuff that you don't want to violate. So the fact that then we were sure it had to be there because otherwise the theories wouldn't work, and it was there, is a real credit to particle physics.
Okay, let's move to the next one. So which of the following inventions was driven by particle physics research at CERN? And we can have touchscreens, the World Wide Web, PET scanners, or all the above, actually. What do you think? And the time is over, and the answer is, yeah, actually, all the above. Yeah. And actually, we are celebrating these days the anniversary of the World Wide Web being born, so I'm sure you've heard about this during today and during the week. Yeah.
Yeah. So it's also a good response to kind of show that fundamental research not only furthers our understanding of the universe, but also has great technological benefits.
Al World Wide Web hi ha un despatx al CERN, que hi ha una placa. La noia que parla exactament està en aquell despatx. La que abans estava aquí a Barcelona.
So they're going around, almost speed of light for 10 hours. What is the distance that they've traveled, do you think?
Yeah, this can be the distance from CERN to the Sun and back, or to Neptune and back, just to the center of Geneva, or the circumference of the Earth.
Yeah.
So, where is it?
And unsurprisingly, it's big. So it's all the way from CERN to Neptune and back. They travel a long way.
Good. And this is our last question now. So, and this is basically about ourselves. So, which is the most common elementary particle in your body? This can be the up quark, the down quark, the electron, or the bottom quark. This is a bit tricky, so think about it carefully. Okay, let's see the answer. What is it? The up quark. So do you guys know why? It looks like
cada protó hi ha un electró i el protó té dos ups i un down.
So basically the reason for this is that, as I'm sure you've heard a lot of times, the human body is mostly water, right? And water is 2 hydrogen and 1 oxygen. So basically the most abundant species in our body is hydrogen. And hydrogen is just 1 proton and 1 electron. But now in 1 proton, we actually have 2 up quarks and just 1 down quark. So at the end, the most abundant particle is the up quark itself. Cool. So yeah, that's it for this test. We hope you have enjoyed it. Maybe we can check how you did. So did you guys can you wave if you manage to answer at least 3 of the questions correctly? Just wave your hands if you manage to do that. Cool. Very nice. So most of the people did actually. Congratulations. Let's check just, what about 5 at least?
I mean, these questions were hard, man. Like, I'm impressed.
Yeah.
Like, for me, would not have done so well.
They were really prepared for this.
Yeah.
Cool. So yeah, congratulations, guys. So I think that's it from our side, isn't it?
Yep, I think it's probably time to wrap it up so we can get going. Yeah, thanks so much for connecting. And just quick note, I did also include in the video chat the thing that I was saying about the high school internship. I just put the link there in the video chat in case people are interested, or you can Google it. But yeah, I hope you guys all had fun and feel like you have learned a bit more about the life of being a particle physicist. And yeah, if you have
any remaining question, I'm sure the people there at your institutes would be able also to give you more information or anything, or if needed, you can always drop us an email, right? So thanks for joining us today. We hope you have enjoyed it. We did, actually.
Yeah, it was fun. Yeah.
It was cool. So yeah, thank you. And we hope to see you maybe in 1 or 2, no, 1 or 2,
Yeah.
3, 4 years, sir. Yeah, let's go for that.
Okay, take care, guys.
Bye, guys. Thank you. Bye.
See you.
Bye.
Thank you.
Bueno, aquí acaba la sessió, vale? Espero que us hagi agradat.